Alright, in this video, we'll be solving the 9709 Pure Mathematics 3, Paper 33, May, June 2025. And for copyright reasons, I will not be displaying the paper, so make sure you have a copy with you to follow along. And before we get into the video, I just want to kindly ask that if you find the videos that we make here useful, please do subscribe and let me know in the comments down below. I know it may not mean like much to you, but this is an indicator to us that you guys are enjoying the content, that it's helping you guys out. So it encourages us to continue making more and more content like this and even better content in the future. So please subscribe. Question number 1, part A. Sketch the graph of y is equal to the modulus of 3x minus 2a, where a is a positive constant. All right. Let's start off by drawing our plane. So I've got my x-axis, I've got my y-axis. Whenever you're drawing a modulus graph, you want to start off by drawing the graph of the straight line first. So we want to draw the graph of y equals 3x minus 2a. And now we need 2 points that lie on this line for us to be able to draw the straight line. So we're going to do when x is 0, when x is 0, y has to be negative 2a. And then we're going to do when x is a, if x is a, y has to be 3a minus 2a, which is a. So I've got the point a. So I'll consider a to be there in the x-axis, and I'm going to need negative a, negative 2a. Okay, so we'll start with this point 0, negative 2a would be here, and then a. So I need a there. A would be here. All right, and then you draw the line going through the 2 points. Like that. And the next thing to do is we want to reflect anything that's below the x-axis, because that's exactly what the modulus function does. So what then happens is that notice that this line is intersecting at negative 2a. So if we reflect it, it has to intersect at positive 2a. Let's just flatten that out a little bit. I think that's fine. Maybe make it a little bit longer to match the right arm. Okay, and then delete anything that's below, or rather erase, not delete, because you're doing this on paper. Okay, so we know that's going through 2a, and then we also need to label the x-intercept here. We need to figure out what that is. So that's going to be whatever the x value is when y is 0, and at the x-axis we know that y is 0. So when is this equation here equal to 0? So 3x minus 2a is equal to 0. 3x equals 2a. Divide both sides by 3. So when x is 2/3 a. So that means that there has to be 2 over 3a. Okay. And label each arm of your graph. This arm came from the straight line, so 3x minus 2a. And then the other arm is just going to be y is equal to negative the 3x minus 2a, all in brackets. And that's the sketch of your modulus graph. Part B says, hence or otherwise solve the inequality, the modulus of 3x minus 2a. Part B, the modulus of 3x minus 2a is less than x plus 5a. So we're going to solve this graphically, because in part A we drew a graph. We already have this graph here. That's what we drew in red. Now we want to draw on the same plane. We want to draw the graph of the straight line y equals x plus 5a. So again, because this is a straight line, we need 2 points that lie on that line. So I'm going to take the point when x is 0, y is going to be 5a. And then we can do the point when, what point do we want to do? We could do A, we could do negative A, we could do, let's do 2A. When x is 2A, we're going to get y is 2A plus 5A, so 7A. All right, so let's see where that is. 0, 5A. So this is 3A, 4A, that's 5A. So 0, 5A is over there. And then we need the point 2A, 7A. So 2A would be somewhere here. And then we want 7A, so 6A, 7A. And so our point has to be, somewhere here. Okay. And so if we join, or we draw a line going through the 2 points, let me just shift it up, rotate it a little bit. Okay, I think that's good. And this there is y is equal to x plus 5a. And notice that our modulus function and the line, they intersect at 2 different points. So we need to solve for those points of intersection. Once we have those points of intersection, we can then attempt to solve our inequality. So let's start by finding this point of intersection. So that comes from this line here and the green line. So that means we have to solve those two simultaneously. So we have negative 3x minus 2a, and that is equal to the green line, so x plus 5a. And again, everything is in terms of a. I know it may be difficult to work with a, right? But just think of it as like any other number, like 1, 2, 3, 4, 5. It's just a constant. Let's multiply through by the negative. That's negative 3x plus 2a is equal to x plus 5a. And move the negative 3x to the other side. So we've got 3x plus x. And then the 5a comes this side. So 2a minus 5a. You've got 4x is equal to negative 3a. Divide both sides by 4. X has to be negative 3 over 4a. Okay. So that means that point of intersection there is at negative 3/4 a. Now we need to figure out what the x coordinate is at this point of intersection. So that's the intersection between y equals 3x minus 2a and again the green line. So we need to equate those two and solve them simultaneously. So that's the 3x minus 2a and the green line, x plus 5a. Move the x to the left. So you've got 3x minus x is equal to 5a plus 2a. So 2x is equal to 7a. Divide both sides by 2. You get x is 7 over 2a. Nice. So that means this here is 7 over 2a. And now we need to solve our inequality. I'm just going to rewrite this with the correct colors that we've used on our graph. So we've got modulus of 3x minus 2a. And we're saying this has to be less than x plus 5a. So this is saying when is the red graph below the green graph? That's what we're trying to figure out. When is the red graph below the green graph? So if I pick this point here, the red graph is clearly above the green graph, so that's not our region. If I pick between our points of intersection, so if I pick this point here, the red graph is in fact below the green graph. So we're interested in that region, and we can just double check by picking a region that's on the other side. So if we're to continue extending this red graph, hope you can see that here the red graph will always be above the green graph, which is now what we're interested in. So clearly the region that we want is between our 2 points of intersection, because that's when our red graph is underneath the green graph. So we can conclude that that's the region between our two points of intersection, so between -3/4 a and 7/2a, and that will be our final answer. Question number 2. Solve the equation 2 ln 2x plus 3 minus ln 2x plus 5 is equal to ln 3x. 4 marks. How generous. Okay. So whenever you're solving a logarithmic equation like this, what you want to do is to make sure that you only end up with one logarithm on either side. So we need to combine these two logarithms into one. The one on the right hand side is already fine. So let's start off by using the law of logarithms that says that n ln a becomes ln a to the n. And we want to use that to move this power 2 up here. And reason being, we want to have the same coefficients on our ln, so we can then combine them in the next step using the next law of logarithms that we'll talk about just now. So that becomes 2x plus 3 squared minus ln 2x plus 5, and this is equal to ln 3x. Okay. And now we can use the law of logarithms that says ln a minus ln b is equal to ln a over b. So that means this is our a, this is our b. So we can combine this to ln of 2x plus 3 squared divided by the 2x plus 5. And that is equal to ln 3x. Now that we've got one logarithm on either side, we can apply the exponential function to cancel out the ln. So it becomes e of this whole thing is equal to e of this whole thing. So the e cancels out the ln, and so you only end up with 2x plus 3 squared over 2x plus 5, and this is equal to, again, the e cancels out the ln, it's equal to 3x. Now we can just get rid of the denominator by multiplying through by 2x plus 5. So I've got 2x plus 3 squared is equal to 3x times 2x plus 5. And let's expand. So square the 2x, that's square the 2, then square the x, so 4x squared. Then 2 times 2x times 3, so that's 12x plus square the 3, that's 9, is equal to 3x times 2x, that's 6x squared. 3x times 5, that's 15x. All right. And now let's move everything to the right. So we've got 6x squared minus 4x squared plus 15x minus 12x minus 9 is 0. So that's 2x squared. Then 15x minus 12x, that's a positive 3x. Minus 9 is equal to 0. And can we factorize this? That's a great question. I think we can. 2x, x, factors of 9. I've got 3 and 3. And then I want to do positive 6x minus 3x to give me a positive 3x. Okay. And alternatively, you can just use the quadratic formula. So we have that either 2x minus 3 is 0, so x here would be 3 over 2, or x plus 3 is 0, so x would be negative 3. And keep in mind that logarithms I draw the graph of a logarithmic function, it would look like this. Logarithmic functions can't actually take in any negative values. So can you see that the graph does not exist when x is negative on this side, right? So if you've got a negative solution, it's not going to work. You can try it out if you punch in ln of, we had -3 as a solution. If you punch this into your calculator, you're going to get an error. So we have to disregard that solution because ln is not defined when x is negative. So we can conclude that therefore x has to be 3/2, and that is our final answer. Question number 3. Very interesting integral. Find the exact value of the integral from a 1/5 pi to a 1/4 pi of 3 cosine squared 5x dx. Whenever you've got a trig function squared, we don't actually want to integrate that directly unless it's like sec squared, because we know the integral of sec squared is tan. But if it's the integral of cos squared, of tan squared, of sine squared, we are going to use trig identities to help us rewrite that, because it's not nice to integrate that directly. So we want to integrate cos squared 5x. I'm just going to start by looking at this identity. Cosine of 2x is identical to 2 cos squared x minus 1. You find this in your MF19. This is a double angle formula for cosine. And the essence of a double angle formula is that the angle on the left should be double the angle on the right. So if I write cosine of 4x, then my angle on the right should be 2 cos squared 2x minus 1, because the angle on the left should be double the angle on the right. So if I want a double angle formula for cos squared 5x, I know that that's going to be on the right hand side, right? I'm going to have 2 cos squared 5x minus 1. The angle on the left has to be double the 5x. So I need to have cos of 10x. And now we're just going to rewrite the cos squared 5x in terms of cosine of 10x, because that's a lot easier to integrate than the cos squared 5x. So let's make cos squared 5x subject of the formula. So that's going to be 1 plus cos 10x is identical to your 2 cos squared 5x. Divide both sides by 2, you get that cos squared of 5x is equal to 1/2 times 1 plus cos 10x. And so what that means is I can come back here and say that instead of trying to integrate the cos squared 5x, I can integrate instead half of 1 plus cos 10x. And this is all with respect to x. So I can write this as the integral from a 1/5 pi to a 1/4 pi of 3/2. So 3 times half, 3/2. And I'll actually just take that outside the integral sign so that I'm left with 1 plus cosine of 10x, yeah, with respect to x. And now this is a lot nicer, and we can integrate this with ease. So 3/2, integrate 1, you get x, plus if you integrate cosine, you get sine of 10x. But don't forget to differentiate your inner function 10x. So if you differentiate 10x, you get 10. So we can divide by 10. And our limits are from a 1/5 pi to a 1/4 pi. And now we can just substitute them in. So that's 3/2. Start with the upper limit. So that's going to be a 1/4 pi plus sine of 10 times a quarter pi all over 10 minus, we'll do the lower limit, that's a fifth pi, plus sine times 10 times a fifth pi over 10. And let's simplify. So let's start by simplifying the upper limit. So that's a quarter pi there. And then we want to evaluate sine of 10 times a quarter pi. Make sure you're in radians. It's 1 and it's being divided by 10. Minus, we've got a fifth pi. And then we want to evaluate sine of 10 times a fifth pi, which is 0. So the whole thing becomes 0 there. So we end up with 3 over 2 times a quarter pi minus a fifth pi plus the 1 over 10. So this is 3 over 2. I think we'll just keep it in brackets. A quarter pi minus a fifth pi, which gives us 1 over 20 pi. And that's plus 1 over 10. And that is going to be our final answer. Question number 4, part A. It is given that Z1 is equal to R1 e to the I theta 1 and Z2 is equal to R2 e to the I theta 2. Show that Z1, Z2 star is equal to Z1 star times Z2 star. Those are a lot of stars. Okay. So, of course, the star means conjugate. So we need to show that Z1 times Z2 conjugate is equal to the conjugate of Z1 times the conjugate of Z2. All right. So let's start with the left-hand side. Right. Let's first multiply Z1 and Z2. So if we multiply Z1 and Z2, that's R1 EI theta 1 multiplied by R2 EI theta 2, right? And so that there is going to be equal to, multiply the moduli, R1 times R2 e to the I, and then add the arguments. So theta 1 plus theta 2. Okay. So remember the rules that say the modulus of Z1 times the modulus of Z2 is going to be equal to the modulus of Z1 times the modulus of Z2. And also in this case, the argument of Z1 times Z2 is going to be equal to argument of Z1 plus the argument of Z2. That's a plus sign, not a G. Okay, so that's why we multiply the moduli, and that's why we add the arguments there. All right, so this is Z1, Z2. So if I put that in brackets, I know that I've got R1, R2, e to the I theta 1 plus theta 2. And what we're actually interested in is the conjugate of this thing. Right. So the conjugate of that is going to be, we just need to make our argument negative. But we'll look at it if I sketch it out. Let's say we've got our real axis here, and we've got our imaginary axis. If I've got, let's say I've got some complex number 1 plus I. That's 1 unit in the real axis and 1 unit in the imaginary axis. 1 plus I would be somewhere there, right? the conjugate of this would be 1 minus I. So it's just a reflection in the real axis, right? So the conjugate would end up being 1 minus I, which is this point over here. Okay, so this is 1 plus I, this is 1 minus I. So what happens is that when you find your conjugate, you're just reflecting in the real axis. You're reflecting the original complex number in the real axis. And if you look at it in terms of the argument, if this argument here was theta, then the argument there becomes negative theta. That's all that happens to your argument. The modulus stays the same, because if you find the distance from 0 to 1 plus I, it's just going to be square root of 1 plus 1, right? Which is 2, root 2. And if you find the modulus of 1 minus I, that's just 1 squared plus negative 1 squared, which is also 1 plus 1 and root 2. So the modulus itself doesn't change. The only thing that changes when you find your complex conjugate is going to be the argument, or if you have it in Cartesian form, then the imaginary part is what changes. But if you're looking at it in Euler form or polar form, then what changes is your argument. Your argument becomes negative. So that means here, all we have to do to apply the conjugate here is make our argument negative. So that means this has to become R1, R2, e to the negative I theta 1 plus theta 2, because here our argument is theta 1 plus theta 2. And we just have to multiply that by a negative sign. And our goal is to show that this is the same as Z1 star times Z2 star. Okay, so Z1 star, I should probably say that this here is Z1, Z2 star, right? Z1, Z2 star. And now we want to find Z1 star times Z2 star. Okay. So Z1 star times Z2 star. So it's the same idea that we were just talking about right now. All I have to do is to make my argument negative, because that's the only thing that changes. So you take Z1, it becomes e to the negative I theta 1. And then this is being multiplied by Z2 star. So you take Z2 and it becomes e to the negative I theta 2, because your argument becomes negative. All right, and so if we simplify this, I hope you can see that we get the same thing. Z star 1, Z star 2 is equal to R1 times R2, R1, R2, e to the, we've got negative I theta 1, negative I theta 2. And if we factor out the negative I there, you can see that R1, R2, e to the negative I theta 1 plus theta 2. And this is clearly the same as that, right? Because our R1, R2, e to the negative I theta 1 plus theta 2 is equal to our R1, R2, e to the negative I theta 1 plus theta 2. And so therefore, Z1, Z2 star is definitely equal to Z1 star, Z2 star. And that is our final answer for part A. Now part B says Z is equal to 3e to the quarter, Z is equal to 3e to the 1/4 pi I. Is a root of the equation z squared plus bz plus c is equal to 0. Okay, so this here is a root of this equation where b and c are real. State the other root and hence find values of b and c. So we know that if you've got a polynomial with real coefficients, then any complex roots occur in complex conjugates. So in this case, if this is a root, then z star also has to be a root. And following what we've been discussing, the complex conjugate there is just going to have the negative argument. So negative a quarter I. This is also a root of our equation here. Okay. And now we need to figure out what b and c are. We've stated the other root is a root. We need to figure out what b and c are. The way we're going to do that is to use Euler's formula, which says that REI theta is identical to R cosine theta plus I sine theta. This is what we want to use. And the reason we want to use this is because I want to convert our roots back to the Cartesian form, back to the x plus iy form. And this will allow us to do that. Once we convert our roots back to the x plus iy form, it's easier for us to then figure out what b and c are. So we'll start with z. We know that z is of the form 3e to the quarter pi I. So this becomes r, our r is 3, cosine of our angle, which is a quarter pi, plus I sine a quarter pi. And so if we simplify this, that is 3 times cosine of a quarter pi is root 2 over 2 plus I sine of a quarter pi, sine of a quarter pi, that is again root 2 over 2i. And so if we expand, we have that z is equal to 3 root 2 over 2 plus 3 root 2 over 2i. This is z in the x plus iy form. Now let's do the same thing, but for our complex conjugate z star. Or rather, in fact, we don't need to do the same thing because I know z star is the complex conjugate of z. So from this form, we can state that z star has to be, you just flip the sign. So 3 root 2 over 2 minus 3 root 2 over 2i. Okay. And now we can, okay, so I'll show you the long way first, and then I'll show you the short way after we've done the long way. So let's start with the long way. So we know that these two are roots to our equation, right? Right, so we know that z is equal to 3 root 2 over 2 plus 3 root 2 I is a root, and the other solution is the complex conjugate, which will be 3 root 2 over 2 minus 3 root 2 over 2i. So we want to reverse engineer the quadratic, which means I'm gonna move this to the left hand side so that I've got z minus, and in brackets put 3 root 2 over 2 plus 3 root 2 over 2i, right? And this is equal to 0 because I've moved that left. And we'll do the same thing here. Z minus, move that to the left, 3 root 2 over 2 minus 3 root 2 over 2i. And this is all equal to 0. And actually, I'm going to multiply through by the negative sign in the first one so that I've got z minus 3 root 2 over 2 minus 3 root 2 over 2I is equal to 0, and the second one becomes z minus 3 root 2 over 2 plus 3 root 2 over 2I is equal to 0. And basically what we're trying to do here is, if you were given some quadratic and you solved the quadratic and you ended up with the solutions x is 2 and x is negative 3, you can reverse engineer this to figure out what is the quadratic that produced this root. And you can do that by saying x minus 2 is 0, moving that there, and x plus 3 is 0, and we've got x minus 2 multiplying x plus 3, and this would have been 0. And now you can just expand, so x times x squared, x times 3, 3x, minus the 2x there, and then minus 2 times 3, that's negative 6, is equal to 0. X squared plus x minus 6 is 0. So this here is the quadratic that produced these roots. So that's the idea we want to use here. It's just that our numbers are a lot bigger, so it looks quite messy. And so now we're going to say that this is z minus 3 root 2 over 2 minus 3 root 2 over 2I multiplied by z minus 3 root 2 over 2 plus 3 root 2 over 2I, and this is all equal to 0. Okay, I'm gonna put brackets here so that you can see that I've got something of the form a minus b times a plus b equals 0, and this is a difference of 2 squares, right? So it should expand to a squared minus b squared is equal to 0. So that means that there becomes z minus 3 root 2 over 2, and that's squared, minus the b, so 3 root 2 over 2I, and that is squared. So now let's simplify this. So square the z, that's z squared, then 2 times z times minus 3 root 2 over 2, so minus 3 root 2z, and then square the last term, so be careful there. Square the negative sign, it becomes positive. Square the 3, it becomes a 9. Square the root 2, it becomes a 2. Square the 2, it becomes a 4, right? Minus, and then here we're going to do something similar. So square the 3, it becomes a 9. Square the root 2, it becomes a 2. Square the 2, it becomes a 4. Square the I, it becomes I squared. Okay. And keep in mind that I squared is negative 1. So I can write this as plus 9 times 2 over 4. Now let's simplify what we have. We've got z squared minus 3 root 2 z, and then I've got 9 times 2 over 4, 2 times. So 9 times 2 over 4 multiplied by 2, that just gives me 9. So this means that, oh, this was supposed to equal 0. This means that z squared minus bz plus c is equal to 0 is this equation here. So we can read off b to be the 3 root 2 and c to be the 9. 3 root 2, and then c is 9. So this is one way of doing it. Alternatively, we can use the theorem that states that if you've got two complex roots, then the quadratic that's formed from these two complex roots is going to be of the form z squared minus the sum of your roots multiplied by z plus the product of your roots. So in our case, we were given z squared plus bz and then plus c. So this b that we have, this b is going to be the sum of the roots, the negative sum of the roots, and then the c that we have is going to be the product of the roots. So if we go back to our two roots and we sum them up and we get the negative value, that's going to be our b. If we take the product of our roots, that's going to give us c. So let's go back to our roots. We can do it on the side. So our roots are over here. If we sum them up, that's going to be 3 root 2 over 2 plus 3 root 2 I. Hopefully you can see that the imaginary parts will cancel out. 3 root 2 over 2 minus 3 root 2 over 2i. So the imaginary parts cancel out and you end up with 3 root 2 over 2 times 2, which is just 3 root 2. Okay, and we said b has to be the negative sum of the roots, so b has to be negative 3 root 2. And I'm just realizing that for some reason there I wrote this as z squared minus bz plus c, but the question clearly states that this is plus bz. So if that's plus bz, it means that b has to be the whole negative 3 root 2, so that has to have a negative sign. So just correct that. Okay. And so from the sum of roots idea, here we get that b has to be negative 3 root 2. And we can do the same for the products. So for the products, let's do it down here. We've got 3 root 2 over 2 plus 3 root 2 over 2i. And this is multiplying. In fact, I think I'm just going to factor out the 3 root 2 over 2 because it's going to be there. Okay, so one of our roots is this, and the other root is 3 root 2 over 2 minus 3 root 2 over 2i. And so we want to multiply these two, but I can write z as 3 root 2 over 2, just factored out, so I've got 1 plus I, right? And we can do the same there. This is just 3 root 2 over 2, just factored out, 1 minus I. And we can multiply these two. So I've got 3 root 2 over 2 times 1 plus I multiplying 3 root 2 over 2 times 1 minus I. Okay. So if we multiply the 3 root 2 over 2 times the 3 root 2 over 2, that's going to give us, this is just 3 root 2 over 2 squared. That gives us a 9 over 2. And we've got 1 plus I multiplying the 1 minus I. And that's just a difference of 2 squares. So I've got 9 over 2, then 1 squared minus I squared. Remember, I squared is negative 1. So I've got 9 over 2, 1 minus minus 1, so 1 plus 1, which is 2. So you end up with 9 over 2 times 2, which is 9, which is the same answer that we got for our C. So this is another way of doing this. Question number 5. The equation of a curve is xy plus y squared e to the negative x is equal to 4. Part A says, show that dy dx is equal to y squared minus y e to the x over x e to the x plus 2y. So this is an implicit differentiation question, and that's because we cannot easily make y or x subject of the formula in our equation. So that's an implicit function, and we have to differentiate it implicitly. So we're going to differentiate the left-hand side. That's the xy plus y squared e to the negative x. And this is all with respect to x is equal to also differentiate the right-hand side with respect to x. All right. So let's go term by term. We want to differentiate xy. That's a product. So first hold the x, then differentiate the other function. If you differentiate y, that's dy dx. Now hold the y and differentiate the x. If you differentiate x, that's 1. Plus, again, we've got a product. So let's start by holding the y squared. Differentiate the e to the negative x. So that's going to be e to the negative x. That's got an inner function, so also differentiate the inner function, which is negative x. So you get a negative 1. Plus, now hold the e to the negative x. Differentiate the y squared. So that goes down, you've got 2y, but also multiply by dy dx. And this is all equal to, differentiate 4, that's a constant, you get 0. So let's simplify. I've got x dy dx plus y minus, that is y squared e to the negative x. And then I've got plus 2y e to the negative x dy dx. And this is all equal to 0. I'll keep everything that has dy dx on the left, everything else goes to the right. So I've got x dy dx plus 2y e to the negative x dy dx is equal to, I'm gonna have y squared, this term here, y squared e to the negative x minus the y. Okay, now factor out dy dx on the left, dy dx and x plus 2y e to the negative x, and this is all equal to y squared e to the negative x negative y. Now let's divide both sides by the x plus 2y e to the negative x. So dy dx is equal to y squared e to the negative x minus y all over x plus 2y e to the negative x. Alright, which is not quite what we want. So we want that. Okay. So we still have to do a bit of manipulation to get the desired result. Alright. So what I'm going to do is I'm going to write e to the negative x with a positive power. So that what we have here is y squared divided by e to the x minus y. And this is all over x plus 2y over e to the x. In both the numerator and the denominator, we want to put everything over a common denominator. So this here has to be, in the numerator, we've got the denominator e to the x. So that becomes y squared. And then this becomes minus y times e to the x minus y e to the x. And this is all being divided by. We're going to do the same thing in the denominator. So put everything all over e to the x. And so that becomes x times e to the x plus the 2y. And I hope that you can see that the e to the x's will just cancel out. Right? Because it's going to be y squared minus y e to the x over e to the x. And I can write this as times. If I change a division sign to a multiplication sign, I have to invert this. So times e to the x over x e to the x plus 2y. And so the e to the x's just cancel out. and we have our desired result. Dy dx is equal to y squared minus ye to the x over xe to the x plus 2y. Part B says find the gradients of the tangents to the curve when x is equal to 0. Okay, they want gradients of the tangents to the curve when x is 0. So the first thing that we need to do, we can't just go straight into our dy dx and substitute x is 0. We also need to know what y is when x is 0. And for that, we use the equation of our curve. Right? So we need to figure out what is y at x is 0. At x is 0, 0 times y, so that just becomes 0. Then we've got y squared e to the negative 0 is equal to 4. E to the negative 0 is just 1, so y squared is 4. So y has to be plus or minus the square root of 4. So y is plus or minus 2. So that means we're going to have two different gradients. We're going to have a gradient at x is 0 and y is negative 2. And that's going to be, so y is negative 2. I've got dy dx is equal to my negative 2 squared minus y, which is negative 2, e to the 0 all over x is 0. So this part here becomes 0 plus 2y, so 2 times negative 2. And if we punch this into the calculator, this is negative 2 squared minus 2 times 1 over negative 4. You get negative 3 over 2. And then we'll do the same at 0, but y is positive 2. So dy dx is going to be equal to as 2 squared minus 2e to the 0 all over the 2 times 2. This time we get 4 minus 2 over 4, which is 1 over 2. So our two gradients are going to be m is negative 3 over 2 or m is positive 1 over 2. Question number 6. Find the complex numbers of z for which z plus 4 over z plus 4i is real and the modulus of z is equal to root 10. Give your answer in terms. Give your answer in the form z is x plus iy, where x and y are real. 6 marks. Okay, so the way we want to approach this question is we want to create two equations in terms of x and y, and then we're going to solve those two equations simultaneously. So we have been told that z is equal to x plus iy. I'll start with this because this is easier. It's going to give us one of the equations and then the other equation is going to come from there. So we know that z is x plus iy, so I'm looking for the modulus of x plus iy. I know it has to be equal to root 10. And so to get my modulus, it's just the square root of x squared plus y squared. And this should be root 10. If I square both sides, I have that x squared plus y squared is 10. So that's one of the equations. We need to find what the second equation is. And for that, we are going to use this second idea that z plus 4 over z plus 4i is real. If I give you a complex number and I tell you that it's real, we know that our complex numbers are going to be of the form a plus bi. So for complex number, if I say it's real, it ends up being a real number. It actually means that the imaginary part is 0, right? That's the only way it's real, because we've got the real part and the imaginary part. So if it's real, then it means that it has to be of the form a plus 0I. The imaginary part has to be 0. So what we can do is we can try to simplify this and figure out what the imaginary part is in terms of x and y, and then we're going to equate that to 0 because we know that this whole expression should be real. Okay, so let's do that. So I've got z plus 4 over z plus 4i. I know that my z is x plus iy, and that's plus 4 over x plus iy plus 4i. So in the numerator, I want my real parts together, so that's the x and the 4. And then my imaginary part is the iy. In the denominator, my real part is just the x, and my imaginary part is the y plus 4. For us to figure out what the imaginary part is, we're dividing two complex numbers, right? So we have to multiply both the numerator and the denominator by the complex conjugate of the denominator. So in this case, the complex conjugate of our denominator is going to be the x minus iy plus 4. So I'm going to multiply by x minus iy plus 4. And this is both numerator and denominator. So x minus iy plus 4. And now it's refusing to switch to red. Now we have to expand. Let's expand our numerator. So I'll start by multiplying my real part x plus 4 with the x. So I've got x times x plus 4. And then the x plus 4 multiplying the negative I times y plus 4. So I end up with negative I x plus 4 times y plus 4. And then now I'm going to do iy times the x. So plus xyi. Then I'm going to do the iy times the negative I times y plus 4. So that gives me negative I squared y times y plus 4. And I don't actually want to expand my denominator because it's literally useless in this question. X plus I, y plus 4 times x minus I, y plus 4. So remember that I squared is negative 1. So we have got negative I squared here. That becomes a positive 1. So now keep in mind that we say that this whole thing that we have, this here has to be real. So that means the imaginary part of this thing has to be equal to 0. So if I can figure out where the imaginary part is coming from, then I can equate that to 0. So our imaginary part is going to come from here because that's where we're multiplying by I. And we know that this imaginary part has to be equal to 0. The reason we can disregard the denominator is because if I'm equating something to 0, right? So let's say I've got x squared minus 3 over x is equal to 0. The denominator can never be equal to 0 because if the denominator is 0, I'm dividing by 0, and that gives us an error. So I'd end up just saying it's the numerator that has to be equal to 0. So I completely disregard the denominator because it can't be 0, right? And so the same idea comes into play here. You can completely ignore the denominator because it can't be 0. So we're saying the imaginary part of this, which is the negative I x plus 4 times y plus 4 plus the xyi has to be equal to 0i. Okay. And so if we just ignore the i's, I have that x plus 4 times y plus 4 plus xy is all equal to 0. And let's expand this. So x times y, ooh, I drop the negative there. The negative should still stay. We're just dividing through by I because we don't want the I. So I should have negative, and then in brackets I've got x times y, which is xy, then x times 4, which is 4x, then 4 times y, which is 4y, then 4 times 4, which is 16, plus this xy there. This is equal to 0. Multiply through by the negative, so negative xy, negative 4x, negative 4y, negative 16, plus the xy is equal to 0. The xy and the negative xy cancel out, so we end up with negative 4x, negative 4y, negative 16 is equal to 0. So we end up with, if I move these two to the right, I end up with 4x plus 4y is negative 16. So that's our second equation in terms of x and y. The other one was that. So we can go ahead and solve these two equations simultaneously. So let's make x subject of the formula in the first equation. You get 4x is negative 16 negative 4y. Divide through by 4. X is negative 4 negative y. So replace this x with negative 4 negative y. So that becomes negative 4 negative y squared plus y squared is equal to 10. And so square the negative 4, you get a 16. 2 times negative 4 times negative y, that becomes positive 8y. Square the negative y, you get positive y squared plus the y squared. This is equal to 10. And if we simplify y squared plus y squared, that's 2y squared plus the 8y. Got 16. If I bring the 10 this side, it subtracts, so it becomes a positive 6. This is equal to 0. We can divide through by 2. So y squared plus 4y plus 3 is 0. And I can factorize this. So factors of 3 that add up to 4, 3 and 1. So either y is negative 1 or y is negative 3. And so because we know what y is, we can figure out what x is. At y is negative 1, x would have to be negative 4, negative, negative 1. So x is negative 4 plus 1, which is negative 3. And then at y is negative 3, we have that x is negative 4, negative, negative 3. So that's negative 4 plus 3, which is negative 1. So that was long. At the beginning, remember we say that z is of the form x plus iy. So that means z has to be equal to either negative 3, negative 1 times I, or z has to be equal to negative 1, negative 3i. And that will be our final answer. Let's move on to question number 7. Let f of x equal 3a minus 5x all over 3a plus 2x times 2a minus x, where a is a positive constant. Okay. Part A says express f of x in partial fractions. So we've got 3a minus 5x, and this is over 3a plus 2x. Don't be intimidated by Cambridge throwing in that a all over the place. Just treat it like you would any other number. It's a constant, so it's like a 2, a 3, a 4. How you treat those is exactly how you treat your small a. So in this case, I'm dividing by 2 linear factors. So that's going to be a over 3a plus 2x plus b over 2a minus x. Then I'm going to multiply through by 3a plus 2x times 2a minus x to get rid of the denominators. So I have 3a minus 5x is equal to a times 2a minus x plus b times 3a plus 2x. And now we'll go through the same procedure that you would typically take when you're finding your partial fractions. We need to find a value for x that will make this bracket 0 to allow me to evaluate b. So I need to find what value of x is going to make this whole bracket 0. So that means x has to be equal to, if you move that side, x has to be equal to 2a. So I can say let x equal to 2a. So that would eliminate that first term. So I've got 3a minus 5 times 2a is equal to b times 3a plus 2 times 2a. So I've got 3a minus 10a is equal to, that's b times, I've got 3a plus 4a, which is 7a. And on the left, I've got negative 7a. This is equal to 7a. b, divide both sides by 7a. And so you have that b has to be negative 1. And we'll use the same idea, but this time for the b bracket, to say what value of x will make this bracket 0. So 3a plus 2x is equal to 0. Then you solve for x. 2x has to be minus 3a. Divide both sides by 2. So x has to be negative 3 over 2a. So we can say let x equal negative 3 over 2a. And so this becomes 3a minus 5 times negative 3 over 2a is equal to, that eliminates the second term. We've got a times 2a minus 3 over 2a. So plus 3 over 2a. And let's simplify this. So I've got 3a. That becomes plus 15 over 2a. And this is equal to 2a plus 3 over 2a, which is 7 over 2a. And that's all multiplying the big A. On the left, I've got 3a plus 15 over 2a, which is 21 over 2a, is equal to 7 over 2a. Multiply both sides by 2 over 7a, right? Reason being, the 7a cancels that 7a, and the 2 would cancel that 2. So let's do that. 2 over 7a. So here we have the 2's cancel out each other, the a's cancel out each other. Then we end up with 21 over 7, which is 3. So you have that a is 3. And so that means if we zoom out, it means our f of x can be written as a, which is 3, over 3a plus 2x, plus b, which is minus 1. So I'll put the minus here, and 1 over 2a minus x. And we have decomposed f of x into partial fractions. Now part B says, hence obtain the expression of f of x in ascending powers of x up to and including the term in x squared. So that means they want us to expand this. So we can write f of x as, if we're going to bring this up to the numerator and this up to the numerator, we can write f of x as 3 times 3a plus 2x to the negative 1 minus, that just becomes 2a minus x to the negative 1. And we have to expand this because, well, that's what they want from us. So to do that, if you go to the MF19, there is the formula that says 1 plus x to the n is equal to 1 plus nx plus n times n minus 1 over 2 factorial x squared, and it continues, right? So we want to use that formula, and we're going to start with this term. We'll do it term by term. We're going to start with 3 times 3a plus 2x, and this is to the negative 1. So what's crucial is that the first term in your bracket is a 1. So we need to make sure that we factor out 3a to ensure that we've got a 1. So I can write this like this. I can factor out my 3a, so that becomes a 1 plus, this is now 2 over 3a x, and this is all to the negative 1. So if I distribute the power, I've got 3 times this 3a is now raised to the negative 1 times this bracket is to the negative 1, right? This becomes 3 times 3a to the negative 1 is 1 over 3a, right? And this is all multiplying our bracket here, 1 plus 2 over 3a x to the negative 1. So the 3's cancel out, and outside the bracket we just have 1 over a times 1 plus 2 over 3a x to the negative 1. All right, so now that this is a 1, we can use that formula, right? In our case, our 1 is the 1, our x, this x here, is going to be the 2 over 3ax. That doesn't necessarily have to be exactly x, it can be some function of x. And then our n is going to be the negative 1. So this becomes, remember everything's being multiplied by the 1 over a, this becomes 1 plus nx, so negative 1 times 2 over 3a x plus n, which is negative 1, n minus 1 over 2 factorial multiplied by x squared, so 2 over 3a x, and this is squared, and remember we're only going up to x squared. So let's simplify this. So I've got 1 over a, and then I've got 1, this becomes minus 2 over 3ax. And let's simplify this here. So that's negative 1, that's negative 2 multiplied by negative 1. So I've got positive 2 over 2 factorial. 2 factorial is 2. So I've got 2 over 2. This part just becomes a 1. And now let's simplify this. So square the 2, you're going to get a 4. Square the 3, you're going to get a 9. Square the a, you're going to get an a squared. Square the x, you're going to get an x squared. All right. And so simplify this. Multiply through by 1 over a. So you've got 1 over a minus 2 over 3 a times a, so a squared x plus 4 over 9 a squared times a, so a cubed x squared. And this here is the expansion for this. It's the expansion for 3 times 3a plus 2x to the negative 1. And now we want to do the same thing, but for our negative 2a minus x to the negative 1. So I'll take it with the negative sign as well. It was negative 2a minus x to the negative 1. Negative 2a minus x to the negative 1. And again, the idea is the same. We need to have a 1 here. So I'm going to need to factor out the 2a. So I've got negative, factor out the 2a. So that becomes 1 minus, and that's now x over 2a. And this is all to the negative 1. Distribute the power. So I've got negative 2a to the negative 1 multiplied by 1 minus x over 2a. Completely omitted the 1. I said 1 but didn't write it. 1 minus x over 2a. And this is to the negative 1 as well. So, in fact, I can remove the square brackets. They're not necessary. So, we've got negative 2a to the minus 1 is the same as 1 over 2a. And this is multiplying our 1 minus x over 2a to the negative 1. And now we can use our binomial expansion formula. So let's just copy that down. How's your day going, by the way? Let me know in the comments down below. Mine's going great. Going great. Doing a lot of math today. Solving a lot of these past papers. So that's good. But anyways, I digress. This becomes negative 1 over 2a times, we want to use our formula, right? So we've got the 1. This here is our x. And this is our n. So it's going to be 1 plus n is negative 1. Our x is negative x over 2a plus n. N is negative 1. Negative 1, negative 1 over 2 factorial. And then x squared. So that's the negative x over 2a all squared. All right. Let's break that down. Negative 1 over 2a times 1 plus, because minus minus, x over 2a. And then plus, this is negative 2 times negative 1. So I've got a positive 2 on the numerator, which is dividing 2 factorial as 2. So 2 over 2. So that's just 1. And here, be careful how you square. Square the negative x, you get x squared. Square the 2, you get a 4. Square the a, you get a squared. And let us expand this. So multiply through by negative 1 over 2a. Negative 1 over 2a times 1 is negative 1 over 2a. Negative 1 over 2a times x over 2a gives us negative x over, that's 2a squared, so 4a squared. And then this becomes negative x squared over 4 times 2 is 8. A squared times a is a cubed. And all of this is the expansion of this bit here. Right, so that bit there is equal to negative 1 over 2a minus x over 4a squared minus x squared over 8a cubed. Okay, let's put everything together. So remember, f of x is just the sum of the two expansions that we've done. So that means f of x has to be equal to, where's our first expansion? This expansion here plus the second expansion here. Actually, let me just copy this because I don't want to get rid of that. And remember that we've factored in the negative sign already. So this negative sign this negative sign that we have there was this negative sign over here. So we've already taken that into account. So now we're just adding everything together. So this is our f of x. Let's simplify any like terms that we have. So we have f of x is equal to, we've got 1 over a minus 1 over 2a. So 1 over a minus 1 over 2a. Put those under one common denominator. So that will be 2a. So this would be a into 2 is 2 multiplied by the 1. So 2 minus 1, excuse me. This gives us 1 over 2a. All right. So that means that there is 1 over 2a. Now let's do the terms in x. So that's the negative 2 over 3a squared x minus x over 4a squared. We can ignore the x's now. We can ignore the x's for now because we know the coefficients. The coefficient there is just going to be x. So that's negative 2 3a squared. And then I've got negative 1 over 4a squared. Again, the idea is the same. Find the common denominator. How many times does this go into that? So that's going to be, oh man, that's not even a common denominator. So find the common denominator, which is 12a squared. How many times does this go into that? It goes in 4 times, multiplied by the negative 2, so negative 8. And then we've got this minus sign here. How many times does this go into there? It goes in 3 times the 1. And so I get negative 11 over 12a squared. So negative 11 over 12a squared x. And now let's do the same, but for the terms in x squared. So this and that. So I've got 4 over 9a cubed minus 1 over 8a cubed. So I need a common denominator. It's going to be 9 times 8a cubed. So 72a cubed. How many times does 9 go into 72? 8 times, multiplied by the 4, so 32. How many times does 8 go into 72? 9 times, multiplied by the 1, so just 9. 32 minus 9, that gives me 23 over 72 a cubed on the denominator. So that means that there becomes a positive 23 over 72 a cubed, and this is x squared. And that will be our final answer. Then part C goes on to say, state the set of values of x for which the expansion in part B is valid. So if you go back to the MF19, the binomial expansion formula we used in part B, the 1 plus x to the n formula, is only valid if mod x is less than 1, which means that if x is between negative 1 and 1. So this is only valid if we used x as negative x over 2a. So if negative x over 2a is between negative 1 and 1, as well as, so and we also used x as 2 over 3ax. So that has to be between negative 1 and 1. That was 2 over 3ax? Yes, okay. So that also has to be between negative 1 and 1. So let's see what values of x satisfy both of these inequalities. So with the first one, let's just start off by multiplying through by 2a. So that becomes negative 2a is less than negative x, which is less than positive 2a. Multiply through by a negative 1, you end up getting that 2a has to be greater than x, which is greater than negative 2a, which of course looks weird, so write it properly. we've got the negative 2a here and the positive 2a here. All right. So x has to be between negative 2a and 2a for this to be between negative 1 and 1. And we have to check the other inequality. So same procedure, multiply through by 3a. So you get negative 3a is less than 2x, which is less than 3a. Divide through by 2. So x has to be between negative 3a over 2 and positive 3a over 2. And now, notice that we said for both expansions to be valid, these two conditions have to hold. So for both expansions to be valid, it means that x has to be between both negative 2a and a, as well as negative 3a over 2 and 3a over 2. So if I put this on a number line, I'm going to have, let's say this is negative 3 over 2a, and this is positive 3 over 2a. If I draw another number line on top and say 3 over 2 is 1.5, so 2a has to be bigger than 3 over 2a, and say that this is negative 2a. So I want both of these inequalities to hold true for my expansions to both be valid. And that's going to be in this region here, when x is between negative 3 over 2a and 3 over 2a. Because if I pick an x that's at this point here, only the x is between negative 2a and 2a will hold. So only the expansion where we used x as negative x over 2a will hold, but the other one won't hold. So our expansion would not be valid then. So we have to say that x has to be between the smaller one, so between negative 3a over 2 and 3a over 2, and that is our final answer. Question number 8, part A. Prove the identity cot squared theta minus tan squared theta is identical to 4 cot 2 theta cosec 2 theta for 4 marks. I think let's move from right to left, because it seems like there's a lot we can do with the right hand side. So if we start with the right hand side, we want to use the identity that, well, we know that cot 2 theta is identical to 1 over tan 2 theta, which would be identical to 1 over sine 2 theta over cos 2 theta, which is just the cos 2 theta comes up top. So cos 2 theta over sine 2 theta. Because here I just want to first rewrite everything in terms of cos and sine, and then see what I can do with that. So I've got 4 times cos 2 theta over sine 2 theta multiplied by, I know that my cosec 2 theta is identical to 1 over sine 2 theta. So I know I'm multiplying by 1 over sine 2 theta. Okay. And so if we simplify this, this is 4 cos 2 theta over sine squared 2 theta. Again, I'm just going to keep simplifying this to sine theta and cos theta, because that's usually easier to deal with. So we know that sine 2 theta is identical to 2 sine theta cos theta. And so what I have is that 4 cos 2 theta is over, we've got sine 2 theta squared. So I've got 2 sine theta cos theta, and this is all squared. So this becomes 4 cos 2 theta over, square the 2, you get a 4, square the sine, you get sine squared. square the cos, you get cos squared theta. All right, and so my 4's cancel out, and now I've just got the cos 2 theta over sine squared theta cos squared theta. All right, so maybe what we can do is, since we are working in terms of sine and cos, let's just break down the left hand side to what its equivalent would be in terms of cos and sine. So we just identify that cos 2 theta is cos over sine. So cos squared theta would be cos squared theta over sine squared theta. So that means what we have, our cos is cot squared theta, minus tan squared theta. This can be written as cos squared, that's cos squared theta over sine squared theta, minus tan squared, that's going to be sine squared theta over cos squared theta. So I know that I'm aiming towards something of this form. So with that in mind, I'm thinking maybe we want to expand cos 2 theta, and let's use the one that says cos squared theta minus sine squared theta, right? Because it looks similar to cos squared theta minus sine squared theta there. And if we do that, we now have that this is cos squared theta minus sine squared theta, and this is over sine squared theta cos squared theta. And we can simplify this by distributing the denominator. So I can have cos squared theta over sine squared theta cos squared theta minus the sine squared theta over sine squared theta cos squared theta. And the cos squared thetas cancel out here, which leaves us with 1 over sine squared theta, which we know is cosec squared theta, which is different from what we want, but okay. Then sine squared and sine squared cancel out, and we've got 1 over cos squared theta, which is minus 1 over cos squared, that's sec squared theta. So we want cos squared theta minus tan squared theta, and for some reason we have ended up with cosec squared theta minus sec squared theta. Are there identities that link cosec squared to cot and sec squared to tan? Yes, they are. So we can use those to help us out. So we know that 1 plus cot squared theta is identical to cosec squared theta. And we know that 1 plus tan squared theta is identical to sec squared theta. Because we know that our final answer should be in cot and tan. So we can rewrite cosec in terms of cot, we can rewrite sec in terms of tan. And so that would then become 1 plus cot squared theta minus 1 plus tan squared theta. So if you simplify, that's 1 plus cot squared theta minus 1 minus tan squared theta. So the 1 and the minus 1 cancel out, and you end up with cot squared theta minus tan squared theta. Alright, and that proves the identity cot squared theta minus tan squared theta is identical to 4 cot 2 theta cosec 2 theta. And that was a lot of work. Now our part B says, hence solve the equation cot squared x minus tan squared x is equal to 5 sec 2x. for x is between 0 degrees and 90 degrees, 4 marks. They said hence, which implies that we have to use information from part A. And notice that our left-hand side here is similar to that. The only difference is that the theta has become an x, right? So that means I can actually just rewrite my left-hand side here as 4 cot 2x cosec 2x. So I can rewrite it as 4 cot 2x, because the theta has just been changed to an x. 4 cot 2x cosec 2x. And this has to be equal to our 5 sec 2x. And now let's just write everything in terms of sine and cos. This should be cosec 2x. Let's just rewrite everything in terms of sine and cos. We know that cot 2x is going to be cos 2x over sine 2x. We know that cosec 2x is going to be 1 over sine 2x. And we know that sec 2x is going to be 1 over cos 2x. So that means this becomes 4 times cot 2x. So times cos 2x over sine 2x multiplied by our cosec 2x, which is 1 over sine 2x. And this is all equal to 5 over cos 2x. So if we simplify on the left, we've got 4 cos 2x all over sine squared 2x. And this is equal to 5 over cos 2x. But if you multiply both sides by cos 2x, this would become 4 cos squared 2x over sine squared 2x, and this is equal to 5. And we know that cos over sine is cot. So on the left, we should have 4 cot squared 2x. So 4 cot squared 2x, and that's equal to 5. And I know my cot squared, my cot squared 2x has to be equal to 1 over tan squared 2x. Feels like we're going in circles. So that's 4 over tan squared 2x. And now we can make tan subject of the formula. So this becomes tan squared 2x is equal to 4 over 5. Alright. And so now let's take the square root on both sides, and we would end up with tan 2x is equal to plus or minus the square root of 4 over 5. So either tan 2x is negative root 4 over 5, or tan 2x is a positive root 4 over 5. So x is going to be arctan 2x rather, is arctan of your negative root 4 over 5. And so 2x, don't simplify just yet, the 2x. So this is arctan of, we are in degrees, so make sure your calculator is in degrees. Arctan of negative root 4 over 5. This is negative 41.810. So this number here that we get from our calculator, this is our principal value. And this is the value we will use to find the other solutions within our given interval. And to do that, we can use this formula PV plus 180 n. And we're going to evaluate this at n is equal to 1. So that's going to be our principal value, which is the negative 41.81, plus 180 times 1. And if we do this, we get 138.19. So I want you to keep in mind that because our principal value is in the form 2x, every solution we get from this calculation is of the form 2x. So here we're saying 2x is equal to 138.19. So even though this may seem like it's outside of our interval, which is 0 to 90, if we divide through by 2, you find that this is actually less than 90 and fits within our interval. So this is going to be a solution within our interval. So divide through by 2, x is equal to, that's 69.1 degrees. Now we want to do the same thing with the other equation here. So we're going to say 2x is arctan of root 4 over 5. And so 2x is going to be arctan of the positive root 4 over 5. You get 41.810. And if you use the same formula that we used, you find that the number that you get is way too big, that even when you divide by 2, it's still going to be outside of our interval. So the only solution we're going to get here is the one from the principal value itself, which is, if you divide the principal value by 2, you're going to get 20.9 degrees. And so we can conclude that the only two solutions that we have within our interval are 20.9 degrees and 69.1 degrees. And that is our final answer. Question number 9. With respect to the origin, all the points A, B, and C have position vectors given by OA is I plus 2j, OB is I plus 3j minus 2k, and OC is 2I minus j plus 3k. Line L passes through B and C. Part A says find a vector equation for L. So remember, a vector equation is of the form R is equal to A plus lambda B, where A represents the position vector of any point on that line. So in our case, since our line is going through B and C, A can be OB or OC. And so this is point, and then B is the direction vector of that line. In which direction is our line going? It's going through B and C, so it's going through the direction BC. So we first need to find our direction vector BC, and we can do that by saying OC minus OB. So BC becomes, OC is the 2I minus j plus 3k, and we want minus OB, so multiply OB by negative 1. So I'm going to get a negative I, a negative 3j, and a negative 2k, so positive 2k. And so my BC has to be, that's going to be 2I minus I, which is I, then minus j minus 3j, which is minus 4j, then 3k plus 2k, which is 5k. And so this is our direction vector BC. So we can conclude that the vector equation of our line through B and C is R is equal to, we need a point on that line. We can use OB or OC, doesn't matter which one you use. Let's use OB. So I plus 3j minus 2k plus lambda times the direction. The direction is BC, which is I minus 4j plus 5k. And that is our final answer. Now B says, the point P is the foot of the perpendicular from A to L. Find the position vector of P. Okay, so let's sketch this out. So we've got L being this line here, that's line L. So let's say our line L looks like this. And we were told that there's a perpendicular that's going from some point A. So I'm going to say A is somewhere here. And the perpendicular is going to L. So this would be our point A. And they've said that the foot of the perpendicular, so the foot of the perpendicular is this point where they intersect, is the point P. Okay. And they want us to find the position vector of P. So how we want to do this is, because we know that P lies on the line L, we can get the general coordinates for P from the equation of line L. If I write line L in component form, right, which is to say my x component, maybe let's change it to column vector form before we go to component form. So I'm going to rewrite this as a column vector, so 1, 3, negative 2, plus lambda, I'll write this as a column vector, that's 1, negative 4, 5, right. So now I want us to write this in component form, which is to say the x component is going to come from saying 1 plus lambda times 1. So 1 plus lambda. The y component will come from saying 3 plus lambda times negative 4. So 3 minus 4 lambda. And then the z component will come from saying negative 2 plus lambda times 5. Negative 2 plus 5 lambda. All right. So this component form actually shows us the general coordinates of any point that lies on line L. So if we want to know the exact coordinates of any point on this line, we just need to know what lambda is at that point. So in our case, I can say that the general coordinates of OP are going to be 1 plus lambda, 3 minus 4 lambda, minus 2 plus 5 lambda. And then to figure out what lambda is, I'm going to use the idea that AP, the vector AP, is perpendicular to a line L. So if I take the dot product of AP and the direction of our line, they should be equal to 0. So we want to use the idea that AP dot the direction of our line L is going to be equal to 0. All right. So we first need to find what AP is for us to be able to do that. So we can get AP by saying AP is equal to OP minus OA, which is equal to OP we know is 1 plus lambda, 3 minus 4 lambda, minus 2 plus 5 lambda, minus OA. OA we know from part A to B, I plus 2j, so that's 1, 2, and k is 0. Okay, so let's simplify our AP. This is 1 plus lambda minus 1, so it's just lambda. 3 minus 4 lambda minus 2, so 1 minus 4 lambda. Minus 2 plus 5 lambda minus 0, so minus 2 plus 5 lambda. This is our AP. And we're saying the dot product of AP and the direction of our line should be equal to 0. The direction of our line is this here, the 1, negative 4, 5. So if I do lambda 1 minus 4 lambda, negative 2 plus 5 lambda, dot 1 minus 4, 5, this should be equal to 0. So lambda times 1, that's lambda. Then I've got 1 minus 4 lambda times negative 4. So negative 4, 1 minus 4 lambda. And then I've got negative 2 plus 5 lambda times 5. So 5 times negative 2 plus 5 lambda. And I know this should be equal to 0. So let's simplify. Lambda minus 4 times 1 minus 4 times minus 4 lambda, that's plus 16 lambda. Then 5 times 2, that's negative 10. 5 times 5 lambda, that's 25 lambda, is equal to 0, right? Now let's simplify this. So lambda plus 16 lambda, that's 17 lambda, plus 25, that's going to be 42 lambda. So 42 lambda is going to be equal to, we've got negative 4, negative 10, so negative 14. But if you move it to the other side, it's positive 14. And divide through by 14. Not 14, but 42. So 42 to make lambda subject of the formula. So this is 14 over 42, that is 1 in 3. So our lambda is a third. So we know that at this point P, lambda is equal to 1 over 3. So we can use that information to get the position vector of P. We know that the general coordinates of the position vector of P are that, but now we know what the actual value of lambda is at the point P. So we can say that this here is equal to 1 plus lambda, so 1 plus a third, 3 minus 4 times lambda, so 3 minus 4 times a third, negative 2 plus 5 times lambda, that's 5 times a third. And so therefore, OP is equal to, let's simplify that, 1 plus a third, 4 over 3, and then 3 minus 4 times a third, that's 5 thirds, and then negative 2 plus 5 times a third, that's negative a third. And actually, let's not be rude. The question gave us the vectors in IJK notation, so let's give them their answer also in IJK notation, right? It's rude to respond to someone in French when they ask you a question in English, right? So 4 over 3i plus 5 over 3j, and then our k component is minus a third k. And that there is our position vector of P. Now part C says, the point D is the reflection of A in L, find the position vector of D. Okay, let us copy our diagram from earlier. I don't need the dot product bit. Okay. Oh my. Okay. So here is our diagram. And we are told that there is a point D, which is a reflection of A in the line L. Okay, so that means D would be somewhere here. And please be careful. I know that my diagram here is like perfectly laid out, but remember that we could have these things off axis like this. So don't immediately think, okay, no, this is straightforward. I'm just gonna make the one part negative, and then yeah, this could be off axis, it could be like this, it could be completely upside down. Keep that in mind. Okay, I'm just doing it this way so that it's easier to see. All right, so we know that D is a reflection of A in L. So what we can do is to say that I know that if I take the vector AP, the vector from A to P, it has to be equal to the vector from P to D. Right, looking at it from the perspective of vectors, AP has to be the same as PD if D is a reflection of of A. And so we can break this down and say that this is AP can be written as OP minus OA, and PD can be written as OD minus OP, right? And we can make OD subject of the formula. So we'd have that OD is equal to, we'd end up with 2 OP on that side, minus OA. OD is equal to 2 times OP. So 2 times OP, what was our OP? I'm going to use a column vector for now, but we'll sort things out in our final answer. 2 times 4 thirds, and then I've got 5 thirds negative a third. 5 thirds negative a third minus OA. OA was 1, 2, and had 0 for the K component. Okay, let's simplify this. So multiply through by 2 there, you're going to get 8 thirds, and then 10 thirds, and negative 2 thirds, and we are subtracting our 1, 2, 0. So 8 thirds minus 1, that gives us 5 thirds. 10 thirds minus 2, that gives us 4 thirds. Negative 2 thirds, negative 0, that's just negative 2 thirds. And so therefore, OD has to be our 5 thirds I plus 4 thirds J minus 2 thirds K. And that is D, the reflection of A in L. By the way, if you like the way that I break down questions and you would like me to assist you with A-level maths, maybe because you're struggling or simply because you want to make sure that you get your dream grades so you get into your dream university, then click the first link in the description down below to sign up for tutoring. You'll be able to book a free discovery call with me, and then we can discuss how best I can assist you, and then we'll start lessons from there. Number 10. The variables x and y satisfy the differential equation sine 4y dy dx is equal to x sine 2y sine 3x. It is given that y is equal to a 12th pi when x is a half pi. Part A. Solve the DE obtaining a relation between x and y. So the first thing you do anytime you're solving a differential equation is you're going to separate your variables. So you want everything that is y on one side and everything that is x on the other. So I'm going to move everything that is y to the left-hand side. So this comes that way. And then my dx is going to come to the right. So I'm going to have sine 4y. Because that sine 2y is multiplying on the right, when it moves to the left, it divides. And our dy stays on the left. We've got x sine 3x. And my dx comes to the right. Okay. And now that we've separated everything, we need to integrate both sides. So if we focus on the left-hand side for now, we're looking at sine 4y over sine 2y, sine 2y, and this is with respect to y. If we go to the MF19, we know that sine 2a is identical to 2 sine a cos a, right? And this is a double angle formula. And the essence of a double angle formula is that the angle on the left is double the angle on the right. So I can also write this as sine 4a is identical to 2 sine 2a cos 2a, because 4a is double 2a. And the reason why this is important is because I want to rewrite my sine 4y there as 2 sine 2y cos 2y, and I hope you can see y, no pun intended, sine 2y. That cancel out, and all you end up with is cos 2y dy, right? So that means on the left, we're actually just integrating cosine of 2y with respect to y. And on the right, we still have our x sine 3x. We'll come back to this in a second. If we integrate cosine of 2y, that's going to be sine of 2y. Don't forget to differentiate your inner function. Differentiate 2y, you get 2, so divide by 2, plus a constant of integration, and this is equal to the integral of x sine 3x dx. To integrate this, now we are going to use integration by parts. So we need to pick a u, and we need to pick a dv dx. To pick your u, use late. So L is logarithms, A is algebra, T is trig, E is your exponential functions. In this case, we've got algebra and trig. So whatever is higher up on the list is what you pick as your U. So in our case, algebra is higher up, so you pick algebra. So in that case, U is going to be x, dv dx, therefore becomes sine 3x. If you differentiate your x, you get 1. If you integrate sine 3x, you're going to get negative cosine of 3x. Don't forget the inner function. Differentiate the 3x, you get 3. And so that means the integral of x sine 3x dx is equal to uv. So this is now just using the by parts formula from the MF19 that says that the integral of u dv dx is equal to uv minus the integral of v du dx dx. This is the formula we're using. So in our case here, our uv is going to be negative x cos 3x over 3 minus, well, I'm going to have minus and then this minus, so it becomes a plus, the integral of 1 multiplied by cosine of 3x over 3 dx. All right. And so the integral of x sine 3x dx is equal to negative x cos 3x over 3. And if you integrate cos 3x, remember we have this 1/3. Let me just write that out here immediately. If you integrate cos x, you're going to get a sine. So sine 3x multiplied by, don't forget to differentiate your inner function. So we have to divide by a 3 as well. So that means the integral of x sine 3x dx is equal to negative x cos 3x over 3. And I've got 1/3 times 1/3. So that's a 9th sine 3x. And that is the integration of that. So that means this part here is negative x cos 3x over 3 plus 1 over 9 sine 3x. So I have that sine 2y over 2 plus c is equal to negative x cos 3x over 3 plus 1 over 9 sine 3x. All right. That's our solution, but we need to evaluate c. Remember, we were told that when y is 1 over 12 pi, x is 1 over 2 pi. And so we can use that to help us evaluate C. So this becomes sine of 2 times y, which is a 12th pi, over 2 plus C is equal to negative x is a half pi, cosine of 3 times a half pi, and this is all over 3 plus 1 over 9 sine of 3 times a half pi. So on the left, we've got that sine 2 times 1 over 12 pi, and that is over 2. Make sure your calculator's in radians. You get 1 over 4 plus C is equal to, then here I've got negative 1 over 2 pi times cosine of 3 times a half pi. So that gives us a 0. So I'm multiplying by 0, so this whole term falls away. And the last term, I have 1 over 9 times sine of 3 times 1 over 2 pi. That gives me a negative 1, right? So I have that C is negative 1 over 9, negative 1 over 4. So C is equal to negative 1 over 9, negative 1 over 4, which is negative 13 over 36. So going back here, we have that sine 2y over 2 minus 13 over 36 is equal to negative x cosine of 3x over 3 plus 1 over 9 sine of 3x. And in this case, they've just said solve the differential equation obtaining a relation between x and y. So you don't really have to make anything subject of the formula. So you can leave it here, and that will be the final answer. Okay, so I've just noticed that we made a mistake. When we were here and we were integrating 2 sine 2y equals 2y over sine 2y, this should have been 2 because it's only the sine 2y's that cancel out. So I should have added 2 here, which is going to multiply this 2 here. So that should have been just sine 2y and nothing else, right? So that means this here should just be sine 2y. And so that means this here should just be sine 2y. And so that means this calculation needs to be fixed as well. So this would just become 1 over 2. And so we end up with negative a half, negative 1 over 9, which gives us negative a half, negative 1 over 9, which is negative 11 over 18. So this here should be negative 11 over 18. And this should just be sine 2y, not divided by anything. So that was a mistake on my part. But the integration on the other side was fine. It was just the sine 2y. All right, so that will be our final answer for the part A. Now part B says, given that y is between 0 and a half pi, find the values of y when x is 0. When x is equal to 0. Okay, so we're using this equation here, and we want when x is 0. So when x is 0 here, we're going to multiply by 0. So the whole thing just becomes 0, right? And then here we're going to take sine of 0. So that part just becomes 0. So the whole right-hand side is equal to 0. So what I end up with is that sine 2y minus 11 over 18 is equal to 0. And so I have that sine of 2y is equal to positive 11 over 18. And so 2y has to be arcsine of 11 over 18. Y in radians because they gave the interval for y in terms of pi. So arcsine of 11 over 18. And we get 0.65746. Right? So that there is going to be our principal value. I'm going to sketch out the graph of sine to see if we've got any other solutions within our interval. So if you're looking for other solutions, use the value that you get straight from the calculator. Don't simplify that just yet. So that should be pi over 2. That's pi. That's 3 pi over 2. And that's 2 pi. Okay. So pi over 2 is approximately 1.57. So 0.657 here would be maybe somewhere here. That's the 0.657. So if I draw a line, I know that I expect a solution somewhere there. By symmetry, I know that this distance here, that's 0.657, should be the same as this here. So that should be 0.657. So if I do, I can say my other solution, which is in the form of the principal value. The principal value is in the form 2y, so my solutions will also be in the form 2y. And then I'm saying pi minus the 0.657. And if we do that, I have 2y is equal to pi minus the 0.657, and I get 2.484. And since this is the only other solution, I can simplify both of them, right? Both the principal value and the other solution that we found. So now we can divide by 2. So I've got y is equal to, divide that by 2, you get 1.24. If we're doing 3 significant figures, divide this by 2. Y is equal to, that's 0.65746 divided by 2. That's 0.329. And so therefore, y is either 0.329 or y is 1.24. And that is the final answer. Now on to question number 11. Number 11, the diagram shows the curve y is equal to root x sine 2x, or x is between 0 and a half pi. The curve has a maximum point at M, where x is equal to a. Part A says show that tan 2a is equal to negative 4a. Okay, so note that a is the x coordinate at the stationary point, right? So this equation is probably coming from saying dy dx is equal to 0. Because we know that at a, that's where we've got the stationary point. So let's differentiate our curve. We've got the y is equal to root x sine 2x. I'll write root x as x to the half sine 2x. We've got a product here, so we'll use the product rule. So first, hold the x to the half and differentiate sine 2x. So to differentiate sine 2x, first differentiate the outer function, which is sine. You're going to get cosine of 2x. Then differentiate the inner function, which is the 2x. So that means you multiply by 2. And now we're going to hold the sine 2x and differentiate the other function. So hold sine 2x, differentiate x to the half. So bring down the half, you get half x. Subtract 1 from the power, you get negative half. Okay, so we have that dy dx is equal to 2x to the half cos 2x, and then we've got plus a half, or rather we can write this as plus sine 2x over 2, and take the x to the negative half to the denominator, so it becomes x to the positive a half. Right, this is our dy dx. Okay, and we know that we are interested in the stationary point, so when dy dx is 0, we also know that when dy dx is 0, our x is going to be a, right? This point here, x is going to be a. So we can replace dy dx with 0, and we can replace x with a. So 0 is going to be 2. I'll now bring back the root sign, so I'll write root a instead, and cos of 2a plus sine 2a over 2 root a. Okay, and now we just have to get creative to see how we can get to tan 2a is equal to negative 4a. So I'm probably thinking that at some point I'm gonna have to use the idea that tan 2a is identical to sine 2a over cos 2a, because I can see that we've got sine and cos, but we somehow need to get to tan. So this is going to be the link that gets us to tan. But I think for now, I just want to start off by getting rid of the denominator. So multiply through by 2 root a. So 0 becomes, that's 2 root a times 2 root a. So we end up having a 2 root a squared situation there. Square the 2, you've got 4. Square root a. The root and the power 2 cancel out, so you just end up with a. So that's 4a cosine of 2a plus sine 2a. Okay, and now the idea that we're talking about has to come into effect. So we can divide through by cosine of 2a, right? Divide this by cosine of 2a, divide that by cosine of 2a, divide this by cosine of 2a. Reason being, the left just becomes or remains as 0. This cancels out, and this here gives us our tan 2a. And so I have that 0 is equal to 4a plus tan 2a. And so that means tan 2a is therefore equal to negative 4a. Now part B says, show by calculation that a is between 0.9 and 0.95. So what we're going to do is we're going to create a function and call that function f of a. We're going to say let f of a be. You're going to take the negative 4a and move it to the other side, so that this becomes tan 2a plus 4a. And what we're going to do is we're going to substitute a with 0.9 and a with 0.95. And we're looking to get a change in sign, because if we have a change in sign, then that means a root must lie between 0.9 and 0.95. So f of 0.9 is going to be tan 2 times 0.9 plus 4 times 0.9, which is, so we've got tan 2 times 0.9 plus 4 times 0.9, and this gives us a negative 0.86. Let's do f of 0.95. So this is going to be tan 2 times 0.95 plus 4 times 0.95 is equal to, so that's tan 2 times 0.95 plus 4 times 0.95. That gives us 0.873, or more importantly, it's positive. And so we can conclude that clearly there's a change in sign from negative to positive. So therefore, since there is a change in sign a change in sign. Our root A lies between 0.9 and 0.95. And that will be our final answer. Now part C says, show that if a sequence of values given by the iterative formula xn plus 1 is equal to 1 over 2 pi minus arctan of 4xn converges, then it converges to A. So what they're saying is that if I carry out all my iterations here and I get a solution from this equation, does that mean that that solution is the same as the solution to this equation from part A? The only way for that to be true is if these two equations are just simply different forms of the same equation. So we have to show that this is just the same equation as the one in part A, because the root we get from the iterative formula would be the same if this is the same equation. So you can go either way. You can go from the equation in part A, proving that it is the same as the iterative formula, or you can take the iterative formula and move backwards and prove that it's the root in A. And I think we're going to do that. So we want to get to tan 2A is equal to negative 4A. So drop the n plus 1s and the n's. So you've got x is equal to 1 over 2 pi minus arctan of 4x. All right. And a total sign for me, or what I'm just going to follow, is that in this equation I have tan, but in this equation I've got arctan. So I just want to get to a stage where I can reverse the arctan to just being tan. So that means I'm going to get rid of the half, the pi, and all of this until I can say tan is equal to that. So multiply through by 2, so that I've got 2x is equal to, now I've got pi minus arctan of 4x. And now what we want to do is I'm going to move the arctan to the left, and then the 2x will come over. So that is positive. Arctan of 4x is equal to, that's going to be pi minus 2x. And then now what we're going to do, so we're going to do apply tan to both sides, so that it's 4x is equal to tan of pi minus 2x. How nasty from Cambridge. So what we can do here is to use a compound angle formula to simplify this. We know that tan of A, in this case it's minus A minus B, is going to be tan A minus tan B all over 1 minus tan A tan B. And the reason I've decided to use this is because I can see that I want something of the form tan 2x, right? Which is that right there. So I need to expand this tan that I have. So that will be 4x is equal to, our A is the pi, our B is the 2x. So I've got tan pi minus tan 2x over 1 minus tan pi and then tan 2x. If you punch tan pi into your calculator, you should find that it's 0. And so we've got 4x is equal to 0 minus tan 2x all over 1 minus 0 times tan 2x. So we just have 4x is negative tan 2x. Then multiply both sides by negative 1. So we've got tan 2x is equal to negative 4x. And then our equation came from saying that when x is equal to a, so when x is a, then tan to a has to be negative 4m. So clearly our iterative formula and the equation in part A are just different forms of the same thing. So if I get a root from the iterative formula, that's also going to be a root for the equation in part A. And now the part D. The part D says, use the iterative formula in part C to calculate A correct to 4 decimal places. Give the result of each iteration to 6 decimal places. All right, let's copy our iterative formula. Okay, and I'll actually just rewrite it as a n plus 1 because we're solving for a minus arctan of 4a n. All right, we need an initial value, so an a is 0, and we can use, when we were verifying that a lies between 0.9 and 0.95, I think I'm just going to use 0.9 as my initial value. You can also use 0.95. You can also use the midpoint of 0.9 and 0.95, which might actually converge faster, but let's just use 0.9. So A1 is going to be equal to half times a pi minus arctan of 4 times A0, so 4 times 0.9. This is 1 over 2 times pi minus arctan of 4 times 0.9, and that gives us 0.920872 to 6 decimal places. Now we want a2, that's half times pi minus arctan of 4 times the previous iteration a1. Here you can just use the ANS button on your calculator. So just go to where you have your 0.9 or whatever your initial value was and replace with ANS, the answer button. That's typically next to the equal sign on most calculators. And don't change anything else, simply press equals. You get 0.91794. And then a3, don't change anything on your calculator, simply press equals. That's 0.918347. Our root, we wanted to 4 decimal places. That's a lot. Okay, let's keep going. Press equals 0.918292. Okay. Is this not it? This is 0.9183 to 4 decimal places. This is 0.91829, so 3. So yeah, we have our root. So A is 0.9183, and that is the final answer. And that's the end of the paper as well. So I hope you found this breakdown useful. If you did, please like the video, subscribe, and let me know in the comments down below what paper would you like to see me break down next. Bye bye.